Now we're going to have a look at the hippocampal system and how the observed properties of the hippocampal system are the ones we'd expect to see in the predicted subsystem that manages change in the modular hierarchy or in the cortex. So in other words, confirming that the primary role of the hippocampal system is determining when and where receptive field changes will occur throughout the cortex. In the discussion of the practical pressures on learning systems, we identified the need for a change manager, and this change manager gets information on the internal activity of columns throughout the cortex, determines which columns are appropriate for receptive field expansions, and sends signals back to the selected columns to drive the expansions. And we also identified a list of specific characteristics we can expect to see in this change manager. One prediction is that the change manager will get extensive inputs from all parts of the cortex and send outputs back to all those structures. And extensive reciprocal connectivity between the cortex and the hippocampus via the cortical areas associated with the hippocampus is indeed what we observe. The exceptions are the primary sensory cortices, the input points for information from the senses. They are not included in this reciprocal connectivity. The primary visual area V1 detects receptive fields that are very specific visual patterns like boundary elements, which probably have a large genetic component in their definitions. The lower degree of heuristic definition means that the change manager is less important. Another prediction is that receptive fields in the change manager will correspond with groups of cortical receptive fields that have tended to change at the same time in the past. The existence of place field neurons in the dentate gyrus, CA3, CA1, and the entorhinal cortex support this prediction. In a novel place, there's going to be a novel relative positioning of objects, and perhaps novel objects, and a range of receptive field expansions will be required. Because the brain is in the place at one point in time, all these receptive field expansions in response to the one place will occur at the same time. So, some of the receptive fields in the change manager will correspond with specific places. Because many of the receptive fields developed to guide receptive field expansion happen to correspond with places, these place fields can be useful for navigation. And when a human navigates an area, even in virtual reality, the hippocampus is very active. The receptive fields that record groups of cortical columns that tend to expand at similar times need to be relatively stable, like the cortical receptive fields. So, as expected, hippocampal neurons are very similar to cortical neurons. Another key aspect of the change manager is that it must continually carry out a massive competition process to identify the currently most appropriate cortical columns for expansion. And the hippocampus has two positive feedback loops in the dentate gyrus and CA3, plus a positive feedback loop between them, and one inhibitory connection. This massive positive feedback structure makes the hippocampus prone to the initiation of epileptic seizures, which are uncontrolled storms of electrical activity across the cortex. So it must have a high system value to justify the behavioral risks, and it implements the competition process, as we'll discuss in more detail a little later. During the competition process, there'll be strong activity, but that activity won't accurately reflect the final selections. So there can't be communication direct from the competition structure back to the cortex. The results of the competition process must be communicated by a separate structure, and CA1 is that structure, and it's observed that damage to CA1 alone blocks all new decorative memories. New cortical conditions need new connectivity, synapses between neurons that weren't previously connected. There isn't time to create this connectivity on the fly when it's needed. So provisional connectivity has to be created in advance. And the brain can't know in advance exactly what connectivity will be needed, so there's going to be some random element in the selections. If the selection was completely random, there'd be a very high probability of creating useless synapses, of wasting resources. But the only available indication of what might be needed in the future is what has happened in the past. And on average, the recent past will be a somewhat stronger indication than the more distant past. So, if two neurons have often been active at similar times in the past, perhaps this indicates a connection between them might be useful. So one way to improve the selection of provisional connectivity will be to take the brain offline and perform a fast rerun of a selection of past experience with a bias toward the more recent. Provisional connectivity can then be established between neurons often active at the same time during this rerun. REM sleep appears to be this partial rerun of past experience with a bias towards the more recent past. Activity of the hippocampus during sleep resembles previous waking activity. For example, if a rat repeatedly runs around the indicated path when awake, and there are two place cells corresponding with 2 points on the path, neuron 2 will often fire after neuron 1 because the rat's in position 2 after being in position 1 as it's running around this path. In the next sleep period, it's found that neuron 2 again often fires after neuron 1, and the sleep rerun appears to be about 7 times faster than waking experience. And it's also relevant that sleep deprivation appears to affect both declarative and procedural memory. And another interesting observation is that immediately after a patient has brain damage that destroys their ability to create new declarative memories, there's often a surge of REM sleep, as if the brain was trying to put more effort into creating resources for recording information. To carry out its primary role, the change manager needs information about groups of cortical columns that expanded their receptive fields at the same time in the past. But this information could also be useful for guiding indirect activations of cortical receptive fields on the basis of past simultaneous expansions. However, there would be no value in recording information about just frequent simultaneous activity when there was no receptive field expansion. So, damage to the hippocampal system can be expected to lead to loss of some types of past declarative memories, but not other types. And it's observed that damage to the hippocampal system, such as occurred in the brain of Henry Molaison, leads to loss of some episodic memories, but not loss of semantic memories, even those acquired in the same period of time from which the episodic memories are lost. So we've gone through the evidence that the hippocampal system is indeed the cortical change manager, predicted by the theoretical considerations. In the next section, we're going to look at the information model for the operation of the hippocampal system in a little bit more detail.